This is question 15 from the SACE Stage 2 Physics Course Companion from Subtopic 3.1, the wave behaviour of light. Here we have monochromatic light incident upon a double slit apparatus. The distance between the slits is 0.2 millimeters, and the pattern is observed on a screen that's 4.3 meters from the slits. The student places a ruler over a section of the interference pattern as shown in that picture. First, we need to work out why taking the measurement over many maxima provides a better experimental value for the distance between adjacent maxima. Now, the reason it's better to take a measurement over lots of bright maxima or dark minima is so that the error in the measurement is sort of spread out over lots of those individual distances between adjacent maxima. So, for example, if you took a measurement over 2 maxima and your error in the measurement was, say, plus or minus 1 centimeter, then that 1 centimeter error is going to be spread over the two adjacent maxima distances that you're measuring, which is pretty significant. But if you still got the error of 1 centimeter measured over 30 maxima, then that single measurement error is spread out over lots of individual maxima. So the overall effect of measurement is much smaller, and when you take the average, you'll get a more accurate result. So if we want to put that into words, I would write that the error in measurement is reduced if a large number of maxima are measured and an average is calculated. So here the important thing is that you mention both the error in measurement and taking the average. One of those on their own isn't really providing a sufficient explanation about why this is the case. Both of those are needed for a proper explanation. Alrighty, so for B, we need to determine the distance between adjacent maxima using the same idea that we just discussed. So here it's a little bit tricky to read, so I'll first look at, no, this isn't really, the first one here at the edge of the ruler isn't really on that left-hand side of the first maxima, so I'm going to take it from the edge of that black, that minima there, and the furthest one we can measure, well, that we can see on the ruler from the interference pattern is probably this one here. Now we can go through and count all of these. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. So here we have 27 lots of delta y equals, now I have to try and read that from each end of the ruler. So on this one, on the right hand side, estimating that, and everyone will get a different value for this depending on how you look at it, but when I look at that, I see about 28.8 centimeters as the upper end. So 28.8, and the lower end here was at about 0.5 centimeters. So take 0.5 centimeters. So here we have 27 lots of delta y, 28.8 take 0.5 is 28.3 centimeters. Therefore, delta y is 28.3 divided by 27, which gives approximately 1.05 centimeters. Now, if you get a little bit different than this, that's likely to be fine. Depending on where you take the measurements, you'll probably get a slightly different result. But if you're getting around 1.05, 1.06, 1.04, you're most likely doing it correctly. Alrighty, so now we have to determine the wavelength of light emitted by the vapor lamp. So we have to look back in the question to see what information we have. We have the distance between the slits is 0.2 millimeters and it's 4.3 meters from the slits. So let's write those down first while we're thinking about it. We have D is 0.2 millimeters and L is 4.3 meters. So we're trying to work out lambda. So we're using the relationship delta y equals lambda L on D. Therefore, lambda equals D multiplied by delta y divided by L. And now we just substitute our values. We have D from the question is 0.2 millimeters, so 10 to the minus 3 meters. Delta y we've just calculated to be 1.05 centimeters, so 10 to the minus 2 meters all over 4.3 meters. And if we substitute that into our calculator, we get about 4.66 times 10 to the minus 7 meters, which looks a little bit nicer if we write it as 466 nanometers. And then we have it. The hardest bit in this question, that explanation is pretty hard for A. B can be a bit tedious going through and counting all of those. This is probably more than you're likely to see in a test or exam or anything like that, so that's fine. But the actual skill is not too bad, and this calculation is just a simple rearrangement and substitution. There's not a whole lot to it. So overall, that was a fairly straightforward question.